This is a dramatic reading of Snarky Puzzle Action Jackson 5 Answers, a blog by the Shand-Up Physicist, available at science20.com. Asking a specific question which has a specific answer is the sign of fertile soil, instead of another shovel full of fertilizer. One question leads to variations on that query. Even a dull question can be informative. Snarky puzzle answers usually have only 4 problems, but for the 5th installment, there is a bonus 5th problem. The August 1st, 2001 blog was entitled Shot in the Head, and here was its snarky puzzle. Develop a small experimental film of all this spin stuff. The current is scurrying along the z-axis, so let it run from -1, 0, 0, minus 0.1 to +1, 0, 0, plus 0.01. So it's going at basically 1/10 the speed of light. Pick an arbitrary point out of the XY desert, say 0.2 and 0.4, and then use some equations that were in that blog to derive the animations. Here's the background. This problem emerges from a discussion of current-current coupling by Feynman. For static, stay-at-home charges, the situation is simple. Multiply the current densities together and be done with it. If the currents move at low speeds, then the current density is really nearly the entire story. But according to Feynman, and I'm quoting here, the interaction between the two currents always involves virtual photons. And that was from his Lectures on Gravitation, page 33. There is a high cost for an odd label, such as virtual photons. Other examples include imaginary numbers, which never sounded real, like ever. Complex numbers will always be difficult. So this question tries to illuminate the physics fairy dust known as virtual particles. Here's my answer. So here is the current coupling sort of fit terms for spin 1, and then below it for spin 2. And you'll notice that the scalars are exactly the same. As a matter of fact, they are invariant under Lorentz transformation. They really are the same sort of thing. But the z part for spin 1, it's just plus or minus jx, jy, whereas for spin 2, it's plus or minus 2jx, jy. And so all I wanted to do was to animate that, choosing these boundaries and giving it a go, and here is that animation. And you notice it's really boring in the y direction because it's 0. It's really boring in the x direction because it's 0. And it's not at 45 degrees, that line in the z plane there, because it's in fact 1/10 of that. It's just crawling up the z while zipping along time, as it were. Because it's going at 1/10 the speed of light. And there are really supposed to be 4 points there. I just want to point that out. All right, so I've got to also make a point of clarification here. That is not really a current, but a current-current interaction. The product of two currents. The Lorentz invariant scalar shows up in Lagrange densities. And then when you apply Euler-Lagrange to that equation in order to get to the field equations, and you take derivatives with respect to the current density. And that basically leaves you with one current density standing in the subsequent field equations. So the scalar interaction term is the same, even if they are about different spins. The contribution from the virtual current to the scalar is negative definite. It must be less than 0 for all non-zero Jx and Jy. The virtual current, in effect, shifts the total current. Both sides of the Z mirror are employed. There's a plus Z and a minus Z. There's nothing in the Jx or the Jy columns. No spontaneous generation of a current, that sort of mice coming out of straw magic trick that some people hypothesized quite a while ago. So everything maps back to the current along the Z-axis. But the animation actually hides data before our eyes. The events plotted in the complex plane are distinct. You can see that symmetry over the Z-axis. But in the animation, one point dominates them all. We take pride in our ability to see in 3D, but then we miss much of what is actually happening along that axis. One must be cautious in what we claim we can see at one time. Such is the plight of analytical animations. Information can be hidden right in front of our eyes. Now, on August 9, I had a blog justifying the love for the strong equivalence principle. And here was the Snarky puzzle. So work with this pathological potential. What are you going to do with that? Well, you're going to actually take a whole bunch of nasty derivatives that I'm not even going to go into. Some involving just plain old the four derivatives and changing the order of it, and taking using hypercomplex multiplication rules. And, well, I claimed it wasn't that bad. Because basically you do it one time, and the rest are, the other 8 are literally variations on that, with different signs for different terms. And in fact, some of the terms just go away. And then I suggested that you take the group you want, point it in a particular direction, 1, 2, 3, 4, feed that group into those 8 quaternion polynomials, and there should be one obvious property for the ones where the gauge, that would be the first term, that scalar term, goes to 0. So here's the background. Why was I asking this question? Massless means what? Well, easy. That's just the opposite of things that have mass. Okay, so mass means what? Well, just use the opposite of the first question. Now, run that cycle until you get exhausted. So here's my answer to that. And it turns out that if you calculate a bunch of these derivatives, like the time derivative of the a part with respect to time, or take the gradient of the phi, or take the curl, they're all 0. Oops! This was so not a pathological potential at all. Half the equations, basically, that I suggested people calculate are always 0. The other half would blink at the spatial origin, some kind of pattern. The patterns would be different, but you really need something more odd to be interesting. So what I puzzled over was an interesting variation to the dull question as asked. Any quaternion function could be viewed as the result of the derivative of some potential if somebody worked hard enough to find out what that potential actually was. So let's ask a simpler question. Compare the analytic animation of U1 to U1 where the scalar has been set to 0. And here it is. And when the scalar is set to 0, the animation blinks. There is only one moment in time when there is information about that function. That moment is now, or time equals 0. At any other time, there is no information available. Perhaps anything that travels at the speed of light blinks in a quaternion animation. Neat if true, but the jury remains in deliberation about that possibility. On August 16th, I talked about visualizing quantum interference, and here was its snarky puzzle. Supersymmetry has super partners to build super friends between particles that take different amounts of time to jog around a unit circle. So go ahead and animate this. Alright, you see that? Okay, so you notice that how long it takes to get around Tx, that would be like 4 pi to get back, to go, as it were. And Ty only needs like 2 pi, and Tz, that combination is going to get around in just pi radians. Okay? Now, if you like a three-way as much as I do, at least in theory, please discuss this thing. You know what I'm saying? All right. So the supersymmetry hypothesis hopes to double the number of particles in the knowable universe. Every boson has a super fermion friend, and every fermion has a super boson buddy. Those that take the normal 2 pi get to hang around and pair up with those needing twice as much rotation, and therefore requires all this supersymmetric mathematics. And what I wonder is whether any of these supersymmetric nerds have ever watched diving in the Summer Olympics, because there are like 3 axes you can rotate around at different rates. And this is what it actually looks like. I mean, I can imagine, the never see nothing defense of spin in quantum mechanics. Half integral spin is beyond the reach of human imagination. So don't even try, you'll simply be misled. Such an approach bores me. I'd rather play, burning through a few million quaternions, see if I see something new out of the process. Now, in that animation there, the spin 1 is like 1 circle. I mean, not a surprise. Spin 2, that's doing a figure 8. The spin 1/2 is a windshield wiper. I don't know. That kind of sounds reasonable to me. Spins can actually point in different directions like they do here. And really the math is pretty much the same. So I said, well, what interaction involves between 2 currents is just taking the product. So why don't I form the product of these 2? And this is what I get. I wasn't expecting this, but it was. You do need to note something though. These are animations of amplitudes. In other words, it's 3 complex values, and those are actually hidden from view in the world of quantum mechanics. What we can see, on average, are the norms formed from the wacky amplitudes, and those look like this. And these are like boring. No, remember, it's made up of the previous one. Honest, that's how I did this calculation. So nature goes again and like hides her data right in front of us, because that really is made out of the same starting stuff as the earlier one. Let me take a lab tech sidebar. I mean, I'm not a theory guy who can talk precisely about what is currently going on in the subject. I'm a lab tech who likes to get and record a large amount of data. I wrote the software that generates those animations, and it writes out to a separate file both the command run and all the quaternions generated by the process. And to me, it's just like a good sign that I need a few thousand data points when blogging about issues on particle physics, a science that uses more data than any other. Just for that collision thing, it required 3,200 quaternions, 3,200, of course, times 4, so, and then each one of those, I think, is like 16 digits big, so it's a long stream of numbers. All right, on August 23rd, I wrote the blog Stephen Weinberg and I had my Snarky puzzle, which involved these, okay? And what I said there was those are the unified gem field equations that I'm supposing might lead to unification of gravity, the weak, the strong, and dm. So I want you to, for the final three there, I wanted them to find solutions to those. And now they look like, look to the 1 over r for inspiration. To my eye, the solutions are beautiful, a nice variation on a 1 over r potential. One up on general relativity. I don't get to say that every day. All right, so the background is that I don't really recall where and when I first wrote out the proof that a 1 over r potential solves Laplace's equation, which is, that del squared phi equals 0. It's basically a rite of passage into the mathematical intellectual elite. Now, elite does not mean a better person or way smarter. It really means that that you're really looking at just a sliver of the human population that has the background skills, and then put the time and effort required to do the derivation. So here is the calculation I did by hand again, who knows, 3 decades or more later. And you can see it just kind of slide by there, and all these factors of half and 3/2, and you get down to that bottom line there, and it cancels out. And even to this day, those cancellations, they just feel like magic. And that's so cool. It's cool even today. So, for my other questions, which were not Laplace's equations, there were variations on that. I mean, they're so similar, you just think, well, why don't I just put in a t with a minus sign and give that a try? And so here I did it by hand again, the old-fashioned way, and you just see factors of half, you see factors of 3/2. And you come down to the end, and lo and behold, they cancel each other out. So if anyone has seen that differential equation or its solution put to use in any context, please give me a shout out. This solution is just so cool and compact. A relativistic variation on the garden variety 1 over r potential. I just want to read up on it, because I'm sure people have probably thought about it somewhere, sometime. All right, on August 30, I wrote the blog on weekly blogging. And here was the Snarky puzzle. Go to a reference library. No, wait, don't bother. Sit down in front of a computer, like you are right now. Open up another tab in your browser. Go to wolframalpha.com. Type in age of the universe divided by Planck length. Save a tree and commit that number to memory. All right, now type in radius of the observable universe over Planck length. Notice that the ratio between the two numbers, the one you just did and the one you did before that, okay? And then skeptically ask the mass of the universe over the Planck mass. See what Wolfram Alpha says for that number. And ramble whether you think that number should be bigger or smaller than the other ones. So you've got age, length, mass. Welcome to the world of dimensionless Planck ratios. Now, in my first stumble in doing theoretical physics all the way back in 1989, I recall babbling about making every number dimensionless. And here I'm finally making that idea from so long ago real. So the numbers are, for the age, they've got it to 3 significant figures at 8.01 times 10 to the 60. The radius is 2.7 times 10 to the 61, or 3 times bigger. Approximately. I guess it's a little bit more than that, but hey. And the mass is 1 times 10 to the 60. It's 8 times smaller than the h. So everything runs away from each other at near the speed of light. Since there are 3 ways to run, the distance of the observable universe is basically 3 times the age of the universe. So that's a little bit of cosmology. The mass of the universe is the subject of ongoing studies. It shows up with just one significant figure and, well, no error bars. They're very confident over there, Wolfram Research. It looks so certain, and also it doesn't show its citations. You know, it's a commercial product, okay? But it was actually really nice to see that the dimensionless Planck ratio mass was less than that of the dimensionless time, just as I'd guessed. All right. Thank you very much.